Bivariate EGF for Stirling numbers. Okay, in my faster videos, I was trying to derive this exponential generating function for Stirling number of first and second kind, right? So this thing over here, this is Stirling number of first kind, right? Stirling number of first kind, and then this is Stirling number of second kind. You might have noticed that the notation is made to mimic the combination symbol, right? And then I guess you guys also know about this exponential generating function for now, right? And the exponential generating function of f of n is just sum from n equals to 0 to infinity of f of n x to the power n by n factorial. In the past two videos, which I will link in description, we derived that this exponential generating function for Stirling number of first kind and second kind were as follows, right? So for first kind, it was n k x to the power n by n factorial. It was minus ln of 1 minus x to the power k by k factorial. And for Stirling number of second kind, it was n k x to the power n by n factorial. This was equals to e to the power x minus 1 to the power k by k factorial, right? And now we are gonna do the Bivariate EGF. So where basically we already have this EGF term and also this ordinary generating function in y. So exponential generating function in x and then ordinary in y, right? I mean exponential in n and ordinary in k. I can say that. Yeah, I think that's more appropriate. Okay. So let's see how we do that. So sum goes from n equals to 0 to infinity. This goes from k equals to 0 to infinity again. Even though I write infinity, this will just be defined for k going from 0 to n. But even if k is n plus 1, we can just define that to be 0, right? If like k is bigger than n, then n, k, this Stirling numbers just can be defined to be 0, and that can help us make sense for any k. X to the power n by n factorial, y to the power k, right? So to find this, what I'm going to do is first switch the sums. Let k goes from 0 to infinity, and this sum goes from n equals to 0 to infinity. And k x to the power n by n factorial y to the power k, right? Now, already know this thing over here. Over here is sum from k equals to 0 to infinity of minus ln of 1 minus x to the power k by k factorial y to the power k, right? And now we can also take y to the power k inside the same power. So we have minus y ln 1 minus x to the power whole k by k factorial. Then now this is just the series of e to the power x, right? So if this whole thing is t, this is the series of e to the power t. So e to the power minus y ln of 1 minus x, right? And now this is e to the power ln of 1 minus x to the power minus y. And that becomes 1 minus x to the power minus y, which was exactly what we had to prove. So it's actually pretty easy because we already had the main result from the previous video. The next one, the series sum from n equals to 0 to infinity, sum from k equals to 0 to infinity of this Stirling number of second kind, x to the power n by n factorial y to the power k. I'm again gonna switch the sums. Sum goes from 0 to infinity, and then from n equals to 0 to infinity, and k x to the power n by n factorial y to the power k. We already know that this EGF in n is going to be e to the power x minus 1 to the power k by k factorial, right? So using that, we have sum from k equals to 0 to infinity of e to the power x minus 1 to the power k by k factorial y to the power k, right? And then we will have sum from k equals to 0 to infinity, and then y to the power x minus 1 to the power whole k by k factorial, and then now this becomes e to the power y e to the power x minus 1. And that was exactly I had to prove, right? So actually, like, proving these two were easy because you already had the main result. But yeah, it feels accomplished, or it feels good, right? To be able to use your results and derive these new beautiful formulas. So, that was it, guys. It was a pretty short video, but pretty important results. And I hope you enjoyed this video. And also do watch the previous videos for more information on these numbers, on their other kind of series, like on their like ordinary generating function, and like some of their properties, also about Bell numbers and things like that. And I definitely believe you will enjoy all of them. So that's it for today, and I look forward to seeing you in the upcoming videos too.